Hello, hi. So welcome to this fifth week lecture on the Q abstract data type. So recall that so far we have looked at uh, lists, doubly linked lists, we've implemented stacks, we've done examples of how useful stacks are, and in today's lecture we are going to look at the Q data type, and we will see as we go through this course multiple applications of the Q data type. But in the sequence of lectures this week, which are three short lectures, we will essentially explore the Q data type. We will do one programming application. We will look at the implementation of the Q data type methods, and then we will have another short presentation on the different types of queues that we typically implement. The reason for the last presentation will be that we will set up a programming exercise which will be uh, in which you will be expected to implement certain features of the different types of the queues that we talk about. So that's therefore today's presentation is going to be about the queue abstract data type, and we will also look at the implementation of the queue abstract data type. That's the focus of today's lecture. It's going to be a short, about 20-minute lecture. All right. So what is the queue abstract data type? So a queue is a first in, first out data structure. It's like a line in a railway ticket counter, and or those of you who have not seen railway ticket counters in this generation, it is like a line in a movie counter where you buy tickets. And if you really haven't been to movie counters, and if you've bought tickets online, then you can imagine a queue to be a queue to get into a metro, or a queue to get into a bus, or queue to get to the examination hall, or something like that. Right? So it's essentially a first in, first out data structure. The person who gets into the queue first gets service first and leaves the data structure or leaves the queue first. So this is quite an obvious name for this kind of a data structure. We are going to see what kind of data we would like to manipulate in a queue-like fashion in this lecture. So let us just look at the methods that are associated with the queue abstract data type. So sure enough, the main operations that we would want to are, we would like to add elements to the end of the queue. We would like to access the element at the head of the queue, and also we might want to remove the elements from the front of the queue. These are three main operations that immediately come to mind when one thinks of a queue, and in particular we will also organize data in a queue-like fashion and service them. We will also see many applications of the queue abstract data type in these three lectures this week. Let us look at the data items and the different methods. So first of all, if you think of a queue in which data is organized in a queue-like fashion, then one thinks of an array, right, which contains the whole queue. The array has a certain capacity. This is an integer valued variable. Then we have an index into the array which we refer to as the front, and an index into the array which is the rear. Now depending on the implementation, index could either be a pointer, right, or it can be a integer value. We also keep track of how many elements are there in the queue by this data item, which is the number of elements. So clearly these are the kind of queries, these are the kind of data items that we would be interested in. We would be interested in the value in the queue, or the set of people, or the set of data items in the queue. We will be interested in how large a queue we can maintain. We are interested in accessing the front of the queue, and to insert elements into the queue, we would like to have access to the rear end of the queue, and we have an integer which represents the total number of elements. Now, the interface methods are the following. The size method is a query which returns an integer value. Of course, it takes as an argument q, and in many of these functions, in these methods, I have deliberately left out the fact that the q will always be an argument. Right? So the argument to this particular method is the q, and the return value is the total number of elements which are there in the queue. The next query is whether the queue is empty, whether it is full. The names immediately suggest that these are two Boolean valued functions that return whether the queue which is passed as an argument is empty or not. peak front is an interesting function. Right? You just look at the element at the top of the queue and you obtain the value. This has its own purposes and we'll see what we can do with this particular function. This is very much like the peak function which was there with the stack abstract data type. NQ is an interesting function. Right? This is a very fundamental central function to the queue data type. We insert an object into the queue, right? And the argument is missing. Right? So in a particular queue, the object O has been inserted into the rear end of the queue. And of course, this operation can fail, and we will see how to implement it so that we get appropriate error messages. Object DQ, right? This method returns an object from the head of the queue, and the end result is that it also removes the element from the queue. So this essentially describes the interface to the queue data type, and these are the data items that we maintain. Let's run an example. Q is the queue in question, right? And the operation that we perform, or the method that is called as NQ5, then 5 is inserted into the queue. When you NQ3, then 3 is inserted to the rear end of the queue. Now if you DQ from Q, then you get the value 5, and what is left in the queue is only 3. If you NQ7 now, then the queue now has the elements 3 and 7. 3 is at the front and 7 is at the rear. Now when you DQ, 3 is the value that is returned and 7 is what is in the queue. Front, yeah, so there is a small error here. This is peak front. When you ask for the value 7, when you look at the front of the queue, the return value is 7, but the queue doesn't change. This is the peak front function. It is a small missing word here. It must be peak front. Now DQ will return the value 7 and remove it from the queue itself. Now if you DQ, an error message is printed. If you ask the question, is queue empty? Then the answer is true. Now when you NQ 9, 9 enters the queue, then 7 enters the queue. Now when you ask for the size of the queue, the return value is 2. Now when you NQ 3, 3 enters the queue, then 5 enters the queue. Now when you DQ, 9 is returned, which is at the head of the queue, and 7, 3, 5 is the contents of the queue. So essentially these are the kind of transactions that are enabled by the interface functions that we have for the queue. The one function that we really did not talk about was the constructor function, or the function that sets up the queue, and we will see it in the implementation. Okay. So now let's look at the implementation of an array-based queue. So let's assume that the queue has n elements. We're going to maintain the queue in a circular fashion, right? And the circular fashion is very important. We will see this again in a couple of lectures time, but conceptually it is very easy. We have two variables that keep track of the front and rear, right? As you can see, the array is indexed from 0, 1, 2 onwards up to n. The shaded portion is the relevant part of the queue. That is where the data items are, and F is the front element of the queue and R is the rear element of the queue. Now you can see that F is not necessarily 0. Right? Now you can imagine why this has happened. So the reason that the elements 0, 1, 2 onwards up to the current F have been DQ'd or eliminated from the queue. Now to be able to check whether the queue is empty or not, because it's a circular queue, we use one location to check that R is empty. Right? So therefore there is one location which is a marker which will tell us whether the queue is empty or not. Now let's just look at the wrapped around configuration of the queue. Right? So the normal configuration is the queue is present inside the array. In the wrapped around configuration, the front element of the queue is here, then the next element is just behind it, and so on. The last element of the array is here, and the next element is here, and the last element of the queue is at the location indexed by 3 in this array Q. And as you can see, R is kept empty. So essentially you can imagine the queue to be a circular queue, right? And there is a well-defined marker as to what the front of the queue is and what the rear of the queue is. In a way, this is an efficient utilization of the space, right? So for example, if you did not have this wraparound configuration, observe that after you dequeue some of the elements, so much space is either wasted or the front of the queue has to be moved to the 0th element. In either case, there is a certain loss. If you have to adjust the queue so that the front of the queue comes to the 0th location, then the program has to do a lot of reorganization work of the queue. This is what happens in real queues or physical queues in the world where people stand in lines. Whenever the front of the queue, right, an element leaves the front of the queue, the element just behind it comes to the head and everybody else moves forward. Right? But in a programming environment, when a program is executing, such an automatic feature does not happen. The elements have to be moved to the front. The other way of dealing with it is to keep a circular queue. Now, for example, observe that if in the normal configuration, if 3 more elements come, then they will be inserted into these 3 locations and the 0th location will become the rear of the queue. And in the meanwhile, if a few elements are dequeued, right, like you see here, and then 4 elements come to the rear of the queue, that is in the wrapped around configuration, this is the kind of picture that you get. So a circular queue actually is a better utilization of the queue data structure. Space is not wasted. Just the array index arithmetic is carefully done to get a lot of benefit from the fact that the queue is organized in an array. The natural limitation that you can see is that the size of the queue is limited by the size of the array unless you can add a few more locations as and when necessary. That depends upon the programming language in which you are implementing the queue. Okay, so now let's look at the queue operations. The queue operations are to return the size of the, let us look at the function which returns the size of the queue. So this is n minus the front of the queue plus the reverse of the queue modulo n. What do I mean by modulo? Modulo is remainder of the division. That is, you take the values, the total n, right? Now you look at r minus f. Now you look at n minus r minus f, in other words written as n minus f plus r, and take the remainder modulo n. Right? So this will essentially tell you how many elements are there in the array. Observe that this is very important. The modulo arithmetic is very important. In the normal case, it is very clear. The size of the array in this case is r minus f. There is no doubt about it. So on the other hand, if it is in a circular fashion, you have to take r minus f, right? Then n minus r minus f, and observe that when you do r minus f, right, you will actually get a negative term, right? Because f is larger in this case than the value of r. Right? Then you subtract out n from it, right? And then 2 modulo n, that will tell you, the remainder will tell you how many elements are there in the queue. That is the size. I encourage you to write. We'll also look at the program which has done this, and I'll also augment to that program when I make it available to you. Here is a function which checks if the queue is empty. If f is equal to r, then the queue is empty. Definitely this is what the condition is when the whole array itself is empty, but subsequently if all these elements, the blue elements, are all dequeued, then f will point to r, right? And that will be an indicator that the queue is empty. Let us look at the enqueue operation. The enqueue operation says that if, sorry, there should have been a double equal to, but it doesn't matter. If the size of the array is n minus 1, then you say that the queue is full. Otherwise, you look at the rear element, insert the object into the rear element, that is in this location, and then increment the value of r by r plus 1 modulo n. Right? This is the crucial thing. Right? That is, when you do modulo, when you come here and then increment it to n plus 1 modulo n, the remainder will point to the first location. So this is the enqueue algorithm. The DQ algorithm is to update the value of f. Right? So when you remove an element from the queue, right, you return the value q of f, that is the f location, that is whatever is at the front, and you increment f to f plus 1 modulo n. Again, modulo means remainder mod n, right? Remainder after dividing by n. So before you write programs, please ensure that you perform this array arithmetic by hand on a sheet of paper so that you become comfortable with this way of indexing into a circular array. Remember that the array is a linear array, but as a programmer, you're using the power of division, right, to actually treat it as if it was a circular object. Right? Therefore, you should not think that the array is a circular array kind of a thing. It is meaningless. The array is essentially a sequence of contiguous locations, that is a sequence of locations in memory which have consecutive addresses, and it is the arithmetic by the program which treats that linear array in a circular fashion. So those were really the methods which are important to us, right? So we looked at the implementation of NQ and DQ to find out if the size, what the size of the array is, size of the queue is, and whether the queue is empty or not. It is very important for us to do the small homework of trying to understand how many operations are taken when the queue is maintained as a singly linked list, right, as an array, and a doubly linked list. Right? So this is left as a small exercise for you to experiment and fill up the entries in this matrix. Of course, the entries of the matrix are not shown to you, but you can see there are 3 columns here, classified into singly linked list and doubly linked list, and the functions are NQ, front, DQ, and is empty, and you can calculate how many operations are performed by the NQ, DQ, front, and is empty functions before answering these questions when the queue is implemented in an array, when the queue is implemented in a singly linked list, and as a doubly linked list. This is left as a small exercise. Let's go to our program now. As you can see, I have also followed some additional discipline. You would notice that the directories are better organized than the earlier lectures. Right? So I have organized the presentation here into multiple directories. This contains all the code, this contains all the documents which are important, this contains the presentations that I'm making, this contains the video recordings, this contains the videos which are uploaded onto YouTube so that you can see them. Right? And the code is present inside this directory called code. And the new additions here are the functions q, qarray.c, qinterface.h, q.h, and I've written a merge function. In this lecture, let us just look at q.h and qarray.c and qinterface.h. As usual, q.h contains the basic object, right? Basic queue object. Observe that it has variables for the capacity of the queue, a pointer to the front, which is an index, a pointer to the rear, which is an index, that is an integer, the number of elements which are present in the queue, and capacity tells you how many elements you can store in the queue, and this is an array. This is a pointer to the actual queue array. The data items are present inside the array pointed to by this variable array. And this object is called this data type is called the queue data type. We will see how to instantiate this queue data type whenever we need it. But now we need to look at the functions which we have implemented. For that, let us look at the qinterface.h. That will tell us what are all the different methods that we have implemented. So this is the interface, right? The interface function includes the q.h header file. Here is the constructor function, the one that creates a queue. Look at the argument. It is a method called createQueue that takes in as an argument a certain capacity, and it returns a pointer to an object of data type queue. The function isEmptyQueue, right, returns a Boolean value. It takes a pointer to a queue and returns 1 or 0 if it is depending on whether it is empty or full. This one returns 1 or 0 depending on whether it is full. Size of the queue returns an integer value regarding the size of the queue. Then we have the methods to update the queue. Like I said when I showed you the presentation, the pointer to the queue is taken, the argument to be inserted into the queue is taken, and it is enqueued into the queue. Dequeue returns an integer and takes in a pointer to the queue from which the integer must be returned, but this also removes the element from the head of the queue. Observe that both these functions really do not give error messages, and this is a drawback, right? Somehow we can, for example, use global variables to actually signal when errors have happened, but that is not something that we are going to do now. But I've already mentioned and I've put the thought into your head saying, how will you actually print or communicate error messages to calling functions when these function calls to either add an element into the queue or delete an element from the queue fail? We will see the implementation though. Now here is a method to look at the front element of the queue. We just peek into the front of the queue, right, and it returns the value. It will not remove this. Now let's look at the implementations of these functions. It's going to be a very crisp look at the implementation of these functions. Almost the pseudocode that we saw in the presentation is what you are going to see here. This is in the file queuearray.c. As usual, stdio, stdlib, and queue.h has been inserted here. Let us just look at the first method. It creates a queue with a specific capacity and returns a pointer to it. Look at create queue. The first thing that it does is it allocates size of queue number of locations, right? And it returns a queue. Therefore, observe that it will create a single queue and inside the queue is an array. And what does it do? It says queue pointer.capacity is equal to capacity. And it says queue pointer.front is 0. Queue pointer.rear is also 0. That is front is equal to rear, that the queue is actually empty. Then queue pointer of number of elements is equal to 0. That is the number of elements in the queue is 0. Now what you do is you get the array to point to an array of integers. How many integers? Capacity number of integers. Therefore, now after this instruction, after this statement, queue pointer.array points to, in the queue, the element array points to an array of capacity number of integers. Now the array has been created. Now you return a pointer. That is it. So now the queue is created. This is the method. Now here is the size of the queue. You just return queue pointer number of elements. Is empty, you check if queue pointer front is equal to queue pointer return. If that expression is true, you return 1, otherwise you return 0. When is the queue full? You check when the size of the queue is exactly queue pointer dot capacity. Right? This returns when the queue is full, and otherwise it returns 0. Note the slight difference. Okay, so here you've seen that we have created a, here we check if we've created a queue in this function, and here we check if the queue is empty. We check here if the queue is full. Okay? And let us just look at the enqueue and dequeue functions. Right? You take an element as an argument, you take a pointer to the queue, you check if the queue is full. Right? If the queue is full, then we actually print an error message here. Right? Remember that we just discussed this a little while back, right? And then you return. Right? However, in a typical programming environment, printing a message is a useless exercise. So we may want to use some global variables which will be used by other functions to check if the queue is full or not. This is a very important programming practice. Such printf statements are very useful only for people who are looking at the execution. A good programmer or a professional programmer would actually find another way of communicating to other functions that the enqueue into this particular queue has failed. One of the ways of doing it is to have a global variable which will store a certain value to record whether the NQ and DQ failed or succeeded. In this case, whether NQ failed or succeeded. So if the queue is not full, then the control comes here. So now what you do is you copy the element into the rare element, then you increment the value of rare by 1 modulo the capacity. That is, we take the remainder by dividing with the capacity, then you increment the number of elements by 1. So this is the NQ procedure. The DQ procedure is very similar, right? So if the queue is empty, then we print an error message, but it is a better programming practice to actually set a global variable so that other methods will know that this particular function call has failed. Okay? Then we return this particular value in element. We increment the value of front by 1 and take the remainder with capacity. Then we decrement the total number of elements. Then you return the element. Peak front is almost the same. You check if the queue is empty. If it is not empty, return the front element of the queue. Do not change any other parameter associated with the queue. Okay? So these are really the functions that we are going to use in the next programming exercise. Okay? And we've seen the implementation of this. Okay? So this has already been compiled. Okay? And I have generated the object. So this has been compiled and the object file has been generated. When we now use it in our merging program, we will indeed take a look at how to compile this object file. We've already seen this. Alright, so in this short lecture, we've looked at all the methods associated with the queue abstract data type, the kind of data items. We've again gone into the good programming practice of defining the queue object appropriately, the queue class appropriately. Okay. Then we looked at the interface functions, then we looked at the appropriate methods, okay, and we have compiled it. So now our queue implementation or the queue abstract data type is ready for use. In other words, we have the .o file, we have the header file, and we are ready to use this queue object in our programs, which is what we will do in the next lecture. So this basically brings to end today's lecture. Thank you.